today we continue our practical on the heart. But before that, you have to mention the properties of the cardiac muscle. Because it's different from skeletal muscle. Last time, we do our experiments on skeletal muscle or the gastrocnemius muscle. Today, we are going to work on the heart. So, you have to know the properties of the cardiac muscle compared to the skeletal muscle. They are anatomically they are different, especially under the microscope. If you see the skeletal muscle, the cardiac muscle is different from the skeletal muscle. As you know, the skeletal muscle, the muscle fibers, cells are nucleus at the periphery. They are all striated muscle. Also, the cardiac muscle is striated muscle. But here, the fibers are separated by sarcolemma, the cell membrane. But in case of the cardiac muscle, they form a syncytium of muscle fiber. That means there is no demarcation. There is junction here, is known as intercalated. In the cardiac muscle, there is the cardiac muscle. There is junction here known as intercalated disc. So the cell is central, located. So there is no, the cells are not separated. They form one syncytium of fiber that when the stimulus comes to the muscle, it will be distributed all over the muscle, and the stimulus is not enough to stimulate the whole musculature. The muscle will not respond. Therefore, we consider the contraction of the cardiac muscle. They follow all or none character. So the contraction will be, the muscle contract only when the stimulus is enough to stimulate the whole muscle. But in case of the skeletal muscle, there is a variation in the sensitivity of the motor units. So they can respond to different level of stimulus. This is why we get sometimes the response will be like that. If you increase the stimulation, you get better and better until you reach the maximum. But in case of the cardiac muscle, the response is always the same. When you get the response, it's always the same because the whole musculature they contract only for the maximal stimulus, which is enough to stimulate the whole musculature. Also, like the skeletal muscle, the cardiac muscle responds to stretching, but it's up to a limit by increase in force of contraction. So when the cardiac muscle is stretched, they respond by increasing the force of contraction, and this is known as Starling law. So the cardiac muscle when it's stretched, they respond to stretch by increase in the force of contraction. The cardiac muscle also is characterized by the inherent rhythmicity. That means even if we isolate the heart from the body, we keep it in a solution, the heart keep on contracting. So even if you cut the heart into small pieces, also each part will continue beating. In this practical, we're going to demonstrate the effect of the factor affecting the heart rate. Start with the temperature. Flood or the heart of the frog is ringer solution at different temperature. At room temperature, you add cold ringer and warm ringer, and you will see the effect on the heartbeat. As usual, we start by section. You have to start by pithing the piece of frog, and then we open the chest and the sternal region, and we expose the heart. We open the pericardium, and we fix the heart with a cape to the myograph, and as we recorded previously in the cardiac muscle, the same way we are going to record the contraction of the heart. We record the normal heartbeat, which is normally in the frog like that. When the heart contracts, it's different. The only difference is that this is relaxation, but when the heart contracts, this is a contraction, relaxation, contraction, and this wave, this is a contraction of the sinus venosus, auricles, and this is ventricle. And usually the heartbeat is initiated in the sinus venosus, and the sinus venosus is considered as the pacemaker of the heart of the human heart. The pacemaker is in the sinus venosus. So the initiation of contraction always starts at the sinus venosus, in this area, and then after that, so this is a contraction of the sinus venosus, then the contraction of the auricle and the ventricle. Relaxation, then another contraction cycle, like that. If we stimulate the muscle, the heart at any time, select the stimulus, we get extra systole, like that. And there is a pause, and the heart again starts contracting. This is first one. This is extra systole. The contraction of the heart is known as systole, and the relaxation is known as diastole. So when you give a stimulus, this is known as extra systole. If you apply any the force of contraction, the heart and the rate, the heartbeat reflect the biochemical surrounding of the heart. So the heart rate is influenced or affected by the temperature, and also it was affected by if we add drugs like adrenaline, which is sympathomimetic drug, acetylcholine, parasympathomimetic, and atropine, parasympatholytic drug. They affect the heart rate and the force of contraction. For example, if we first usually start by recording normal heartbeat at room temperature, which is, for example, like that. Then after that we add we add cold ringer, and then we record the heartbeat. Then we add warm ringer solution. When we add at low temperature, the heart rate decreases, and when the temperature increase, the heart rate and the force of contraction also increase. Usually, we can calculate the heart beats by referring to the speed of the recorder. The paper speed, for example, if the speed is 1 centimeter per second, so that we measure, for example, 2 centimeter, 1 centimeter equivalent to 1 second. So we measure 1 centimeter. And then we count the number of beats in 1 centimeter. So for example, if I hit 1, 2, 3, 4 beats every second, that means in 1 second, 4 beats, 4 heartbeat. Click 60 seconds. We just multiply. This is just an example. You just measure, for example, 1 centimeter, and then you count the number of beats in 1 centimeter, and you multiply by 60 to get the heart rate per minute. So we have to record the normal heartbeat at room temperature. Then we add cold ringer, and when we add warm ringer solution, and to compare the heart rate at the 3 different temperatures. Also, using the same way, we add adrenaline, acetylcholine, and atropine, and we observe the changes in the heart rate. Usually, adrenaline increases the heart rate, and acetylcholine decreases the heart rate. If we add atropine, it will reverse the effect because it's antidote for acetylcholine. So the heart rate will resume again beating after addition of atropine. So we're going to start the demonstration by section to expose the heart of the frog, and after that we fix the heart to the micrograph and we record using the physiograph. Between the skull and the first cervical vertebrae for breathing, then we push the needle and we push it forward, backward. Okay, when the needle is in the right trap, the hind limbs paralyzed. Okay, then we fix the flock. The flock board. open the chest. And this generation. Expose the heart. The heart is beating. Okay, this is a truncus arteriosus. This is a ventricle. You open, remove the pericardium. You have to be careful. You know, the heart is free. Okay, we fix the hook to the apex of the heart. We have to fix the heart straight to the live graph. Okay. Now the heart is beating. Normal heartbeat. So. recording the normal heartbeat at room temperature. It's normal heartbeat at room temperature. Normal heartbeat at room temperature. Then we start to see the effect of temperature on heartbeat. And then we apply cold ringer solution to the heart. See the effect of cold ringer on the heart. The heart slow down because of application of cold ringer. So if we want the heart to resume back, we normally have to add warm ringer. Now this is, we are applying warm ringer. We apply warm ringer solution to the heart to see the effect of warm ringer on heartbeat. Now the heartbeat increase, the rate of beat increase, and contraction is a bit powerful. This is the effect of temperature on heartbeat. Okay, stop. Okay. At room temperature, Then we add ice cold ringer. This is the heart slow down. Then again we add warm ringer, and again the heart rate increase. If we want to calculate the heart rate, you see here, this is the speed, 0.25 centimeter is equivalent to 1 second. So 1 centimeter is 4 seconds. So this is this distance from here. This is 1 centimeter. From here, for example, from here to here, this is 1 centimeter. This is 1 centimeter. 1 centimeter is 4 seconds because the speed 0.25 equivalent to 1 second. So 1 centimeter equivalent to 4 seconds. So in 4 seconds you have 1, 2, 3, 4 beats. In 1 centimeter we have 4 beats when it's cold at room temperature. So when it's cold, you see here, from here, when you add the cold ringer, 1, 2, 3. We have only in 1 centimeter, we have 3 beats in 1 centimeter, which is equivalent to 4 seconds. 4 seconds. Then we go back here. We come after we add the warm ringer. See from 1 centimeter. 1 centimeter. 1, 2, 3, 4, 5. We have 5. Or in 1 centimeter, we have 5 beats. So it is easy to calculate. After that, you can calculate how many beats per minute. It will be more accurate if you, for example, if 1 centimeter is 4 seconds. If we take 2 centimeter or 5 centimeter, it depends on the records available. So it will, if you take, the error will be less, and the difference will be clear. For example, if you take from here, this is when we apply the cold ringer up to here. Let us see this how many centimeter. 1, 2, 3, 4, 5, 6. This is 6 centimeter. So we can compare 6 centimeter for each group. 6 centimeter means 24 seconds. So we'll see the beats in 24 seconds, and we can easily calculate the heart rate in 1 minute. So this is the effect of temperature. We are going to demonstrate the effect of drugs on the heart rate. So starting from here, you consider this one the normal heartbeat. So let's give adrenaline. Then we are going to add adrenaline. Effect of adrenaline on heart. After you add adrenaline, the heart rate increase and the contraction seem to be more powerful. This adrenaline. Add the adrenaline. Stop. Okay, stop. Acetylcholine, start. The effect of acetylcholine. We're going to add acetylcholine to the heart. You see the effect of acetylcholine, the heartbeat. Okay, be ready. Okay. So you add acetylcholine. Acetylcholine slow down the heart. Acetylcholine, as you see the effect on the heart is slow down. So once stop, we have to add atropine so that stop. The heart stop. We wash the acetylcholine. Set the heart and adding atropine. Again, quickly bring me the syringe. We add atropine to stop the effect of acetylcholine, and the heart again resume beating very fast. So the atropine antagonized the effect of acetylcholine. Acetylcholine stopped the heart. Maybe we add overdose of acetylcholine, but now it is again resume beating as normal. Okay, here we show normal heartbeat. After that, we add adrenaline to the heart, and the adrenaline increases the heart rate, and even the power of contraction increase. Then we add acetylcholine. The acetylcholine reduces the heart rate, and maybe because we had overdosed, the heart stop. Then again, we try to wash the acetylcholine and we add atropine. The atropine antagonizes the effect of acetylcholine, and the heart again resume contraction as normal. Properties of cardiac muscle. We mentioned that the heart, the cardiac muscle has inherent rhythmicity. That means it can beat even if we isolate the heart from the body. It will keep on beating. You see here the heart keep on beating. This is known as inherent rhythmicity. Inherent rhythmicity. Inherent rhythmicity. So that means the rhythm of the heart is still there, even it's isolated from the body. If we cut in small pieces, also still it will keep on beating. For example, see here. Let us cut the ventricle. If we cut in small pieces, also keep beating. The pulse will keep. See? Still eating independently. This is inherent rhythmicity. The heart block, we are going to block the transmission of excitation from the sinus venosus to the other part of the amphibian frog by tying a thread. We call it stenosis ligature between the sinus venosus and the atria. As you see here, this is normal recording, but after we tie the thread, you will see the block of transmission of excitation, and the heart will stop. The only part beating will be the sinus venosus, and after a time, the other chamber resume beating. Okay, ligature. I'm going to tie the first sinus ligature, and to see the effect of ligature on the heart beat. Okay, then tie. Okay, sure. Here. You see now, after the first ligature, the beating of the heart changed, because this is the only beating of the sinus venosus, because we block the. But after a time, it will start resuming. Now we are going to tie the second ligature, which is between the atria and the ventricle. So after a time, the heart will start contraction again. Now it's the ventricular contraction start. One time, the ventricle now start again to contract after the second ligature. This is ventricular. These are the ventricular contraction. Come after time. This is another ventricular contraction. Continue. Okay, good stuff. This record demonstrates the application of stance ligature, which shows the block of the transmission of excitation from the sinus venosus to the auricle and ventricle. So when we tie the first ligature, this is normal heartbeat. When we tie the first normal ligature, we get only the beating of the sinus venosus, like that. So after, this is the first stance ligature. Here we apply the second ligature. This is just due to when we tie the ligature, it jerks. But after a time, the ventricle start to contract. See here, this is a ventricular contraction after the second application of the second stance ligature. This is normal heartbeat, normal beats. This application of first stance ligature. Ventricular sinus venosus contractions. Here, this is the second ligature. After the second ligature, these are ventricular contractions. It's ventricular. Now this is ventricular. This, you see, they become close ventricular contraction. Sincere gratitude and appreciation to Professor Dr. Muhammad Ali Rajion for giving me the opportunity for recording these practical classes. And also, I would like to thank Mr. Zulhilmi for the cameraman, and Mr. Kufli Pinchaknoor for the technical assistance. And also I would like to thank Brother Johari and Kwan Zainab and Kwan Rasmawati for the preparation during the practical classes.